Hey, what's up everybody, and welcome back to the Sanctuary. I'm Professor C, and today we're going to continue our series on anatomy and physiology. Today specifically, we'll be talking about inorganic chemistry. Let's check out some inorganic molecules and what the concept inorganic means versus organic. First rule is that if you are considered inorganic, not organic, you are not a hydrocarbon. Okay, so let's stop for a minute. Hydrocarbon simply means that you contain both H, hydrogen, and carbon. You must have both hydrogens and carbons in your molecular structure. So if you are a hydrocarbon, you are considered to be organic. If you are not a hydrocarbon, you are inorganic. So let's take a peek here at some of the big classes you hear about. Acids and base, like look up here at this sulfuric acid, H2SO4. It shows the symbol, shows a little model of it, but the important thing is it a hydrocarbon? Does it have hydrogens? Yes, it does. Does it have carbon? No, it does not. Therefore, it's not a hydrocarbon. Therefore, sulfuric acid is inorganic. You can do the same thing with a base too, but we'll talk about that chemistry in a little bit. All right, let's take a look at salts. Looks like NaCl up here. And we saw that in our discussion of ionic bonds and so forth. But the point here is salt, NaCl, sodium chloride, is not a hydrocarbon. It does not have carbon, nor does it have hydrogen. So it fails on both of those fronts. So it is not a hydrocarbon. Salt is not. Therefore, it is inorganic. Water. Again, organic, inorganic has nothing to do with whether it's good for you, bad for you. That's not what we mean here in this sense. Water has hydrogen, but it has no carbon. So water is not a hydrocarbon. Therefore, it is inorganic. Water is inorganic. Carbon dioxide, over here at the last panel, CO2. Well, it's got the carbon part, but no hydrogens. So it's not a hydrocarbon. Therefore, it's inorganic. It's not organic. Salts. Okay, a salt is an ionic substance, or a compound, if you'd like to use that word, that forms crystals, and those crystals will dissociate in water. Now, another word you can use for this dissociate is ionize. So dissociate means to break apart. So does ionize. It means to split into your ionic components. We're going to look at a few examples of that in a moment. Once those crystals break apart, the ions now are called electrolytes, and they will conduct electrical current in a watery solution. There has to be a watery soup for that to happen, but in a watery solution or a watery soup, salts will break apart and conduct electricity. Things like sodium and potassium that have a lot to do with generating electrical impulses in cells. Chloride has something to do with many things, but a chloride shift is something you see when you talk about blood physiology and blood chemistry. Iron being a big component of heme, which is a component of hemoglobin, which is a large component of red blood cells. Calcium, of course, used for muscular contractions and some other things, stored in the bones. So we see a lot of these inorganic substances like salts playing very special cellular roles. Okay, water everywhere. We've seen it before in previous lectures. We're going to kind of make the same points that is always made about water. Most of you, being that you are made of cells, is water, about 70-ish%, right? Somewhere between 60 and 80 is what you see. So 70 would fall in the middle. But why? Well, there's several properties. We talked about, water runs metabolism. I bet we're going to find that on this list, but let's run through the other characteristics too. We use it as a major transport medium like the blood. A large component of the blood is water, and so it's an easy way to move things from one part of the body to the other, just like we talked about the cardiovascular system being like a system of rivers that delivers necessary substances to and from tissue. High heat capacity. Again, we're not going to get into this too much in any of the lectures, but it takes a while to boil water, right? It doesn't just start to boil instantaneously. High heat of vaporization, that has something to do with when you sweat and physical water evaporates from your body, and this cools you through a process called evaporative cooling. So high heat capacity and high heat of vaporization are important, but less important than probably water allows metabolism. We saw that a lot when we talked about chemical reactions, that you need water to both make bonds and break bonds. It goes both ways. Okay, water is a polar solvent. We've mentioned this before about the polarity of water, and water is very good about dissociating, or again ionizing, ionic substances like salts. So if you take a salt and you put it in water, you should get ions. Let's draw that out real quick. Okay, let's take our old friend NaCl. Let's take our old friend table salt, sodium chloride. And you do see it represented here in this picture on the right. You see a big yellow and green crystal of salt. And you see little water molecules that are blue and red tearing apart the crystal ion by ion. So what you can do is you can say, take some of this, put it in some water. Because we know a lot of times you add water, we get bonds to break, and that's exactly what we're going to do here. So we get sodium ions and chloride ions. If you look really closely here at this image, you'll notice that the blue balls are touching the chloride, and of course that would be the hydrogen part. And remember that the hydrogen is the slightly electropositive part of that atom, and that's why it's attracted to that negative chloride ion. Conversely, up here you have the sodium portion, the sodium ion part of the crystal that has ionized, and you see the red parts, the oxygen part, remember, being slightly negative, and it will encircle the positive sodium ions. This is showing how water ionizes salts into its ions, and once the ions are present, they'll then conduct electricity. Okay, acids and bases are also, and again you can look over here at the chemical formula for sulfuric acid, and it's got hydrogen but no carbon, so it's inorganic, and it will play a similar role that a salt does when you put it in water. So acids and bases also dissociate or ionize. Remember, we can use the word ionize there in water. They split apart into their ionic components in a watery solution. Important to remember that. Once they have split apart, those free ions are called electrolytes because now they conduct electrical currents just the same way that salt did when we broke the crystals apart into their ionic components. Let's draw this one out real quick. Let's take some hydrochloric acid, which is really easy to sketch. It's just HCl. And let's put it in some water. Sometimes you can show the chemistry like that to show that we put this acid into a watery solution, and what's going to happen? Well, it's going to dissociate, it's going to ionize, it's going to break apart, because that's what acids do when you put them into a watery soup. They break apart into their ionic components. So what will you get? Well, you get H pluses, which are hydrogen ions, and chloride ions. And then, of course, those free ions, now called electrolytes, can conduct electrical currents. Well, what about the base, you say? Well, let's draw out the base in a similar way. Sodium hydroxide, Na. There's the sodium. Hydroxide is just an OH, and sometimes you see it written different ways, but we'll just do right like that. NaOH, sodium hydroxide. Let's put it into a watery solution. What's going to happen? Well, sodium hydroxide is a base, and it will dissociate, ionize in a watery solution. So it should go and break apart into sodium ions and hydroxide ions, which are going to be negative. I'll put a little negative charge on the O just because it looks more correct in my eyes. So whether it's an acid or a base, if you put an acid or a base into water, it should dissociate into its ionic components and then conduct electricity, just like the way that a salt did. All right, so let's pretend that you're working in a lab and you've got some hydrochloric acid and you spill some on the floor and you think, oh, I got to clean this up before my boss sees me or I'm going to get in trouble here. So what should you do if you spill acid all over the floor? Now, you may think, if you're in a panic, that you should just get some water and you should throw that on there and that'll help clean it up quicker. But we just looked what happens when you put an acid in water. You get ions, and basically you're spreading out the acid across the floor even more. You're helping the acid to spread. You may be diluting it a little bit with the water, but you're helping those components move around. So the strangest thing that you would think to do is pour some base on it, which is weird, but let's see what happens here. This is called a neutralization reaction, and let's just draw it out before we talk about it more. So let's take our hydrochloric acid. All right, and we spilled it on the floor, right? Well, instead of adding water to it, let's add sodium hydroxide. Right? It doesn't make sense at first, but since we've taken chemistry class here in the sanctuary, we know about this. Okay, so there's a strong acid, hydrochloric acid, a strong base, sodium hydroxide, and we're mixing them together and we're hoping we do it before our boss gets here. And we want to neutralize not just that strong acid, which is going to burn a hole in the floor, but that strong base is going to burn a hole in the floor too, maybe. And we need to turn them into something less dangerous, if you want to use that word, less caustic. And what you're going to have happen is sometimes this is called a double exchange. And I'll write that right here. Double exchange reaction. We didn't talk about this. Okay, what happens when you put these together is the H from the hydrochloric acid will hook up with the OH from the sodium hydroxide, and the sodium will hook up with the chloride ions. So what you have is kind of a double switcheroo. These two guys will hook up, and these two guys will hook up. And so we've taken a very strong acid and a very strong base, and we put them together, and they had a double exchange reaction. And what did we make over here? Well, that's just water and salt. We made salt water, and we can easily mop that up with some towels or a mop from the closet before the boss gets in there and sees the mess we made. So even though it doesn't make sense at first, if you know a little bit about chemistry, a strong acid and a strong base can neutralize each other and become harmless substances like salt water because of these neutralization or double exchange reactions. As usual, thanks for watching. If you want, check out the other videos in the series. See you next time. Bye-bye.